Good afternoon. We are going to start lesson 18, which is on a new subject. It's a new module on sequence control. So we are going to have our first introduction today on sequence control, on the kinds of controllers that are used for sequence control, namely programmable logic controllers or PLCs, and we are going to take a first look at the programming languages, the languages which are used to specify control programs for PLCs. So as usual, we will first look at the instructional objectives. So after learning the lesson, the student should be able to state three differences between analog and sequence control. This is important because traditionally an electrical or manufacturing or chemical engineering student is typically exposed to analog control, while the kind of control that we are considering here are different in nature. So it's important to understand the differences between analog control and sequence control. Obviously, we should know, she should be able to give an example of industrial sequence control, an actual practical example, and he should, the programmable logic controllers are controllers which are primarily used in the industry to implement sequence control. He should be able to know three of its major functions, the major functional characteristics. He should also know the major components, the major structural components of the PLC, and he should be able to describe a typical program execution cycle that takes place in PLCs and how these program execution cycles affect the control performance. And finally, he should be able to know what are the typical elements of a relay ladder logic program, which is one of the programming languages which is used for programming a PLC, and know the various interpretations of the symbols used in this language. So first of all, let's try to understand what is sequence or logic control. So as I said, it's fundamentally different, not fundamentally, maybe very significantly different from analog controls on various aspects. So we need to understand what it is. So I constructed an this is my definition, words are mine. So it's a class of control problems for systems where inputs, outputs and feedbacks are discrete set valued. Actually, I would rather say that they are, for the purpose of control, it is taken that they are set valued, that is, the intermediate values are not considered. So for example, a switch, it stays 99.999% of the time in on state or off state, but obviously it goes from the on state to the off state, and that timing is so short that we choose to ignore it. So we say that a switch is a system which stays in either one of two states. So it's either on or off. We actually choose to ignore the times when it is going from on to off, because it's too small and of no consequence for us. So in that sense, the inputs and outputs and feedbacks are discrete set valued, like on off. And the problem is to cause or prevent occurrences of either particular values of outputs or combinations of outputs. So when the switch 1 is off, switch 2 should not be on. So give an example from daily life. If let's take a daily life example of a railway crossing. So if the incoming train coming sensor is on, then the gate should be off. So some particular combinations are allowed, and some particular combinations could be prohibited. So the purpose of control is to ensure that in all future behavior of the system, those combinations of outputs either must occur or cannot occur as is specified. Similarly, we could also have timing restrictions. So, you can say that after the train coming sensor becomes on, within 1 minute the get close sensor should become on. So, now you are giving some timing restriction. So, you must ensure that the system, that the gate becomes closed within 1 minute of the train coming sensor becoming on. We might also like some given sequences of outputs, right. So, for example, suppose let's take a buffer where some machine is producing parts and then putting them in the buffer, and the buffer from time to time gets emptied. So, the states through which the buffer goes, so maybe the buffer capacity is 2. So, and every time the machine is dropping a part, the buffer is getting filled. So, the buffer should never go to the overflowing states. So, it should go to part count 0, part count 1, part count 3, then empty part state, and then again come to part count 0. So, the buffer should only go through certain states and should not go to some other state. So, only some particular sequences of outputs or events should be allowed, or there could be some given orders between various outputs. So, after this occurs, that must occur. So, these are sequencing orders, sometimes also called interlocks. If this has already occurred, that cannot occur. So, this kind of, so basically what we are trying to say is that if the system states are assumed to be discrete, this kind of statements are made about the desired behavior of the system, and then the problem of control is to realize them by exercising the inputs to the process. So, this is typically a sequence or logic control problem. Why they are called sequence or logic control? Because it is a finite state thing. So, it is described more by logical methods than by numerical methods. Before we look at them in more conceptual ways, let us take an example. So, look at this. This is what is it? It is supposed to be a die. It's supposed to be a stamping press. So, if you look at this, then so this is the stamp. This is the press. Okay. So, there are two solenoids, up solenoid and down solenoid. So, if the up solenoid is energized, these are hydraulic presses. So, if the up solenoid press is energized, then the pressurized fluid flows through this path and goes into the machine. So, the machine is constructed in such a manner that then this press goes up. Similarly, if the down solenoid is energized, then this press goes down, and this, so this is your metal sheet. It comes down and stamps on it. So, it keeps stamping, retracting, and creating a particular shape of sheet metal. These things are typically used in making, let us say, car bodies, right. So, it is a hydraulic stamp press. Okay. So, and obviously after so what happens is that it goes up, the up solenoid may be de-energized. So, whether it has reached the topmost position or the downmost position, this needs to be sensed. So, there are two sensors. This is the upper limit switch and lower limit switch, and these are the two actuators. The down solenoid and the up solenoid are the actuators, and this thing is our system. So, this is a typical example of a sequence control problem, where we are interested in only, see, the system is, everything is analog if you look fine enough. So, obviously the piston cannot the system cannot instantaneously come down from the up to the down state. But what we mean is that for the control of this system, we are not interested, for the sequence control in this of this system, we are not interested to know the intermediate states. We want to only ensure that if this machine is supposed to stamp, if that command is given, then it should periodically come down and then go up, come down and go up. So only that, we are only interested in, that is our control problem is only to ensure that it periodically goes through the up down sequence, that is all. So in this sense it is a sequence control problem, right. So this is, there are n number of such other problems. For example, there are many other application examples. For example, a plant startup shutdown sequence. So when a plant is started up, initially you have to bring up levels to start. Initially automatic control may not be immediately applied. So first you have to, you know, maybe fill some chamber, so then start the pump. So first open the valve, then you start the pump, then once the level starts filling, then you see when it has reached some sufficient level, then you switch off the pump, then you switch off the valve. So basically, and then you start the heater, so let the temperature come up, then maybe the automatic control will start. So initially for these startup shutdown sequences, nobody, I mean you may not be interested in doing an analog controls, but rather the system is actually operated based on discrete controls. Similar things happen for shutdown sequences. So once things have to be shut down, there are certain such, you know, some discrete control actions have to be taken. So for such things, typically sequence or logic controllers are used. Let us say conveyors. Conveyors are very widely used material handling systems. So in conveyors you don't bother about what is going to be the motor speed. Maybe you don't bother about that. So you only have to start the conveyor or stop the conveyor. Maybe when you detect a part on the conveyor, you will start it. If you then after the part goes out from the other end, then you stop it. So conveyors are typical examples where a lot of, you know, very simple PLC controls take place, sequence control. Similarly, there could be automated assembly operations. So for example, you have a pick and place robo. So the robo, you know, it goes through certain states. So maybe it is situated somewhere and it's going to the picking up item X from the left hand side of the workspace, then putting it on the machine, then operating the machine, then again picking it up, then putting it on the bin which is on the right side of the workspace. So the overall sequence through which a robo goes, or maybe picks an electronic component, places it on the PCB. So such operations are typically described and controlled by sequence controllers. Now we must understand that this is actually a robo. When it's for its movement, it has very sophisticated controls. It has servo motors in its various joints. It has analog controls on all of them. But here we are thinking of designing the controls at a different level, where we are not interested in that speed control loop is actually in place and it is working, but at a lower level. So only this sequencing tells us that what set point to give at what time. So it is a kind of, you know, set point sequencing if you look at it from the analog control point of view. So based on the sequence of the digital controller or the discrete event controller, corresponding analog set points are being downloaded on the analog controllers, and the analog controllers are actually taking place and controlling the motion of the robo and then taking them through the final states. So as far as the sequence control problem is concerned, we are not interested in knowing or in describing or in solving how a robo arm is moving from one point xy to another point x1 y1. We are not interested in that. We are just making a mechanism by which the proper sequence of commands can be specified to the analog controllers, and then the analog controller will be expected to take care of that motion, right. So in this sense, it is actually a supervisory control problem. So sequence and logic problems are often applied at a supervisory level, to provide set points to the analog controllers which are working below it at an automatic control level, right. So, similarly sequence control in CNC machines, where depending on the geometry of the part to be cut, depending on the machine configuration, sometimes you have to move the bed this way, sometimes you have to move the bed that way, sometimes you have to extract the spindle up, you may have to change the tool, you may have to switch on some lubricant flow. So, various kinds of again supervisory control actions must be specified. In fact, in a PLC there are, I mean it's if you see a CNC machine controls, then you can very clearly see that there are two different control systems, usually on two different control processors. So, you generally have a high speed microprocessor or a DSP, sometimes generally microprocessors, which take care of the analog controls problem, which are much faster, actually control the various motors. And you have a PLC, generally, I mean GE Fanu or whatever, I mean some make of PLC, and which will basically control these various motions and maybe also monitor the machine. So, supervisory control of robos, as I have told. So, sequence, that is why PLCs are used hugely in I mean this kind of discrete event control problems are very common in actually in industrial processes, and I mean you will find, I mean literally hundreds of them. Now, we must realize, since we are, I thought that since we are this is a new kind of control problem, and we are the same motor or the same robo about which we learnt from an analog control point of view, we are still using them, but now trying to construct completely different types of models for them and trying to solve different types of control problems. It is useful to understand that a model of a process is actually, I mean what kind of model you will construct for a process entirely depends on what is it, which aspect of the system behavior you actually want to capture. So, it is not always, so for example, let us say, imagine that if you are trying to model a computer, then there are various architectural models for a computer. For example, there may be a von Neumann architecture, there may be a reduced instruction set architecture, there are several well known architectures of computers, I mean models around which computers are constructed. Now, computers are typically very large digital circuits, I mean sequential digital circuits, which are sometimes thought of as state machines. So state machines are again there are various kinds of state machines. So when you are seeing the computer at the state machine level, then you are using models like Milli machine, Moore machine, basically automata theoretic models. So again, these state machines are made of what? They are actually made of digital circuits. So digital circuits, how do we describe digital circuits? We know that we describe combinational digital circuits using Carnot maps or sum of product Boolean formula, or if they are sequential circuits, then we describe them as state transition tables. So now what are digital circuits made of? They are made of transistors. Now transistors are actually, the moment you come to a transistor, you have come down to the analog level. So there you start describing voltages, currents and their time behavior. So you have various kinds of small signal network models, either low frequency models or high frequency models. We have learned several kinds of models. Again, transistors are made up of semiconductors. So semiconductors have physical models, electrons, holes, energy bands. So you see that, but you obviously will not describe a state machine as a set of transistors. So everything, so there is a whole hierarchy of abstractions. So as you go up and up, you consider more and more things, and you consider them in more and more abstracted ways. But sometimes it also happens that the same device is being looked at as something by one person and by another thing as another person. For example, say if you are the user of a digital circuit, then you will use a model like that of an AND gate or AND gate or flip flop. So you use one kind of models. But imagine the semiconductor, imagine the gate designer, the VLSI designer of the gate. So why you look at a gate not as transistors but as a digital circuit? Because you know that the circuit is such that for most of the time, just like the switch example I gave, it will either stay in a 5-volt state or a 1-volt state. So it's either 0 or 1. So it suffices to describe when it will go to 0 and when it will go to 1. It is not important at all to describe the transitions of how exactly the voltage signal will rise from 0 to 1. That's not important at all. On the other hand, the person look at the VLSI designer who wants to design the gate. So the gate circuit is such that it will automatically go from 0 to 1 or 1 to 0. But the beauty of design or the whole credit of design goes into understanding that how fast you can make it rise, how much less power can be dissipated and things like that. So on the other hand, the circuit designer is mostly concerned about the transition part from 0 to 1. So he obviously cannot take a view of the same gate as that of an AND gate model. He has to take a view of the same device as a nonlinear transistor circuit, because his attention is focused only on the transition or on the analog behavior, right. So it's important to understand that. So therefore, this is what I am saying, that even for industrial processes there is obviously analog behavior, everything is analog. But if we know that the analog behavior can be taken care of by the analog controls which exist at a lower level, then the problem can be simplified. If we assume the existence of suitable analog controllers, then the problem can be simplified to that of only specifying certain discrete commands, and how those commands will be realized, that is taken care of by something else. So we are not interested in modeling that. Therefore, we will simplify the models and use different models and then solve sequence control problems. That's the whole idea, right. So it's very important to understand that. If you look at continuous variable models, there the signals are real valued. Actually you have an infinite number of possibilities of values, and time is sometimes continuous, sometimes discrete. So when we have continuous time models, then we have time continuously varying. But for all practical implementations, especially using computers, we must discretize time. That is, we must consider values only at certain instants of time. Now you must realize that we are discretizing the time axis. We are not discretizing the variable value. Variable value axis is still continuous. Variable value can be anything. So, but the time axis is sometimes discretized. So that's why it's called a continuous variable models, where variables can take any value. Contrary to this, in discrete event models, which we are going to use for sequence or logic control problems, typically the values of variables that we'll consider will be considering finite. So let us say a typical example is on, off, some tank level, low, medium, high. So we are not interested in knowing how many meters. We are only thinking that the tank is in the tank level could take one of 3 symbolic values. So each of those symbols actually represent some kind of an analog level value range. So if it is 0 to 2 meters, we just call it low. We indicate it by a symbol low. If it is 2 to 4 meters, we call it medium. And if it is 4 to 6 meters, we call it high. So we may define a control problem where we are not interested in knowing the value, but we are only interested to see that the moment the water level falls from high to medium, start the pump. So we are interested in specifying such things. So so discrete values over finite domains, and therefore we have what is known as the finite state space. So the combinations of variables that can exist in a system are going to be finite. Similarly, time, we have two kinds of models. This we are not going to see too much, but we have two kinds of models called synchronous and asynchronous, where we assume that all variable changes also occur at along with some clocks, just like a master slave flip flop is a synchronous device. So or sometimes we have asynchronous. So at any time certain variables can change. So it's like time discretization here. So if the time is, if variables can change from one value to another value at any point of time, we call it asynchronous. If it only happens at certain periods of clock ticks, we call it synchronous. So this is the, so once we quantize, once we create a discrete, this kind of discrete finite state description of the system, then it is easy to construct the, then we can construct the behavior of the system. So typically we have in such systems three kinds of variables. They are the input variables. Input variables are some things which are applied externally. Okay. Then there are output variables, and then there are state variables. So output variables are something which we can maybe sense or see, and there may be some other variables which we cannot see, but the system goes through them. Okay. So typically we consider systems, and in most of industrial control problems we have only a finite number of system states. Now these states, what is behavior? Behavior is the pattern by which states change from, the system continuously moves, evolves from one state to another. Now why should the state change? The state could change either by an external event. So a room was in dark state. Now somebody comes and gives an input or changes an input variable, say a switch from on to off to on. So as a consequence of this, the room state goes from dark to lighted, right? So this is a state change caused by an external events. Sometimes systems also go by, because of their internal dynamics, without any other external input given, it might change its state, right? So there may be some arrangement in the system by which, suppose after it is made on, let's look at a mono-shot timer. There is a common electrical examples. So there may be something that once you press it, some bulb glows up, and then its dynamics is such that again after some time by itself, without any input being applied, it will come down. So state changes are sometimes caused by external events and sometimes caused because of their own internal dynamics, they might come down. Similarly, state changes also, at every state there are some outputs which are exerted by the system. So as states change, as the system goes from one state to another, the outputs are also changed, and these outputs changes are perceived in the external world, and they are sometimes called events, right? So you could have events or outputs caused by state changes. So this is, so when we have to describe a system, we'll presently see an example. We have to basically, whenever we want to model a system for the purpose of logic or sequence control, we have to find out which are the variables, which are the input variables, which are the output variables, how those change, what input exertion causes what state change. So basically if we can describe these, then we have got the system model. Now in any control problem, there is a, just like in analog control, you have an open loop plant and you have a closed loop plant. So you have a plant by itself, which is called uncontrolled or open loop, and you also have a closed loop plant which is controlled. So the controlled plant is actually does not exhibit all possible behavior of the open loop plant, but exhibits only a certain subset. So that's the job of the controller. So we have to specify, if we are talking about the controller design problem, then there are two things that we have to do. The first thing is that we have to say what this system does by itself, what it is capable of doing, that we can get from its model. Then we have to give a specification, that is, of all this behavior we do not want some behavior, so we want only some of them. So what is the behavior that we want for the controlled system? That is called the specification. So these specifications could be again stated in various ways, for example by transition event sequences, which could be either timed or untimed, or by saying that giving the enabling conditions for some transitions, that is we may like to cause some transitions in certain ways in the system. So in various ways system specification will be given, and then the job of the controller design is to ensure that this system actually behaves like the specification system. That is the problem of discrete event or logic or sequence control. So seems a bit abstract perhaps, so let us see an example. So in our old example, what are the external inputs? So depends on what you have. I mean you actually have to see. So maybe that you have in this system we may assume that it has three external inputs. One is the up solenoid, another is a down solenoid, and the third one is a master control switch. So these are the three input variables. They are all external to the system. And each one of them, for example the up solenoid and the down solenoid may take two values, either 0 or 1. So what could be outputs? For example, we could say that corresponding to limit switches we have some lamps. So whenever a limit switch is made, we have an up lamp and a down lamp. So they are like indicators. So corresponding to the limit switches we are having some outputs, up lamp and down lamp. Similarly, the machine we assume is existing in three kinds of states. Basically they are the motion states of the system. So the system could either be in the idle mode, in which it is doing nothing, it is not in the active mode, or so we can say that whenever the master control switch is 1, what is the effect of this external input? That it will make the system from the idle to any one of these, and if it is off, then from any one of these it will actually come to the idle state. This is what we are trying to describe the behavior of the system. So otherwise among the active states the system could be either in moving up. So it is moving up, it is neither up nor down, the position of the press is neither up nor down, neither down nor up, it is somewhere in the middle, but it is moving up. Similarly it could be moving down, or it could be not moving but it is in the up position or in the down position. So we have chosen to model the system in such a manner. So we assume that the system goes through such states. Now state changes, what are the typical state changes in the system? For example, we say that the external inputs are MCS, up solenoid and down solenoid. So if MCS is exercised, system comes from idle to any one of these. Maybe it comes from idle to down, and if the up solenoid is pressed and if the system is in the down state, from there if the up solenoid input is exerted, then it will go from the down state to the moving up state. So these are cases where a state change is caused by an input. We'll presently draw a diagram. Similarly, internal for example, let's draw this diagram. So the system we are saying exists in 5 states. Okay. So maybe this is up, this is down, this is moving up, and this is moving down, and somewhere here you have idle. So when you get, so how does the system change states? So you have from idle to down, when MCS equal to 1, you are trying to describe the system behavior, and then from down, if you give an up solenoid, then it goes to the moving up state. From there, by internal dynamics, after some time it will go to the up state. In the up state, if you give it a down solenoid equal to 1 input, then it will be moving down state, and then by itself it will come to the down state, right. In between, sometimes self loops, that is you can write that in between, if moving down is in this position, it will be in the moving down state, because it might take quite some time for it to come down from up to down state. So, and then we can say that from anywhere, if you go to moving up, then it goes to idle. If MCS becomes 0 at any point of time, then it goes to the idle state. So you know that we are basically graphically we are describing how the system goes from one state to another because of various external inputs or because of internal dynamics. Okay. And similarly, we can say that, for example, we can have the various outputs. So if we have the 2 outputs, so here we will have down lamp is equal to 1 and up lamp is equal to 0. Similarly, here we have DL equal to 0 and UL equal to 0, both are 0. Here UL equal to 1 and DL equal to 0. So these are the outputs. So at the various states, these are the outputs which are actually exercised, and which may also be sensed by the sensor for the purpose of the controller. Now this is the behavior of the intrinsic plant. So now one has to ensure somehow that the specification that you give for the system, that is actually first up solenoid is exercised and it is held till it goes to the up state, and then when it goes to the up state, then the down solenoid is exercised. So this is the desirable cycle of the machine. So one has to exercise, some device has to actually compute this, when to apply this up solenoid and when to apply this down solenoid, and it is the controller which is going to do that. So right. Similarly, as we say that events are caused by state changes, because this we have already, for example, in moving up lamp is equal to 0. When there is a state change from moving up to up lamp becomes 1. So state changes also cause outputs. And a system specification, as we said, that what is the objective of the machine? The objective of the machine is that when the control switch is on, at that time it must come down, go up, come down, go up. This it must do a certain number of times, till the MCS switch is put off. If the MCS switch is put off, immediately from there it must go to the idle state, which we can describe. What is the position of the place at that time, whatever it is. So the system specification for this system could be an alternating sequence of up and down states. So it must continuously go from up to down and down to up states. So having done this example, we can take a look at some basic differences between sequence control and analog. So, firstly, the process variables in the sequence control are discrete valued, in analog they are continuous valued. The model, as a consequence, the model here is logical, typically state transition kind of models, while in analog control they are numerical. So, you use either differential equation or you use difference equation. So, use some equation with numerical equations. Similarly, the signals, generally the signals indicate some status. So, something is on, off, maybe a traffic light is either red or amber or green, or we are interested in, or they are sometimes signals are in this case sequence of symbols. So, it goes from up, down, up, down, up, down, or maybe a conveyor for a buffer, another part, buffer empty, another part. So, these are sequences. So, another part is an event occurring whenever another part comes into the buffer, and in between certain other event called buffer empty takes place. So, the signals, by signals we mean the sequence of these events in the case of sequence control. On the other hand, we know that in the case of analog controls, we want to specify actual trajectories, we want to specify properties of trajectories, rise time should be less than something, maximum overshoot should be less than something. So, what are we trying to say? We are trying to say that we are trying to describe some properties of the continuous trajectories in terms of their values, while in sequence control we are interested in either status of some signals and their sequences over time, right. Oops. Similarly, if you look at control here also can be open loop or closed loop. Closed loop control is possible even for discrete event or logical control. For example, in our die press example, we had those two limit switches. So, any controller that will work can take feedback of the state of the process using the limit switches and then decide the control input. So, in that sense, logic control can also be feedback control, right. But it is generally on off or logical kind of control, and they are generally supervisory in nature. That is, they are used to decide, in many cases they are used to decide the command sequences, which are again realized in turn by the automatic controllers. While in the automatic controllers we could have linear or we could have non-linear controllers, and I mean which are actually working at an automatic control level. One very interesting design is, of course, since you have so much simplified the state space or the values that signals can take into 2, 3 or 4 codes. So the models are much simpler. So, for example, very linear, non-linear differential equations can then finally give rise to some 5, 6, 7, 8 or maybe 20 state finite state machine, which is a much simpler model compared to the nonlinear differential equation. So, generally design is order of magnitude simpler than continuous automatic control designs. One interesting thing is that tuning is generally not needed, because the models are generally not physical. They are actually abstract, information oriented models. So, unless you change the strategy of operating the plant, the controllers need not be tuned, while in the case of automatic control, because system heat transfer coefficient will change, pipes will develop sludges inside, valve characteristics will change, reactor characteristics will change. So, therefore, automatic controllers continuously require tuning from time to time, but these sequence control controllers, they generally do not require any training, any tuning frequently, because processes, till you do not have a different automatic control system which will take different inputs, or you want to change the whole operating mode of the process, there is no tuning of the sequence or logic control law to change. So, now we have perhaps understood the discrete event control problem. Now this is not new. It used to be, this kind of problems have been handled in the industry long time, even before the microprocessor came into existence. So previously what people used to do is that people used to use relays and contactors to actually realize this kind of logical functions, you know. So that's why previously such logical functions used to be called relay logic. In fact, the name relay logic diagram, relay logic ladder, these are basically legacies of that past, which are still being used. Of course, they are gradually getting changed, and probably after 5-10 years relay ladder logic may not be so relevant. People will find other graphical and other ways of describing these programs. But it's a fact that PLCs have actually, as they started to replace the relay logic, and so why they are better than relay logic, that we can see. For example, relay logic is hardwired. Actually things are put, relays, contactors, they are actually connected, right? While PLCs, the logic is actually in a program. So while if you want to change the logic little bit, then you have to dismantle relay logic, at least some parts, and then again install a new one. While in the case of PLCs, because it's a microprocessor device, all it takes is to change the program, right? Therefore, these are, you know, relay logic is actually difficult to upgrade and maintain, while PLCs are very modular. You can just take out one and you can put it another, you can all the time put, you know, you can expand your system very easily. You can buy new input output modules. You can then simply plug them into the racks without any problems. You know, these are much more industry friendly to upgrade and maintain. Relay logic is obviously much more limited in terms of size and complexity, because you have to construct them using physical relays. While PLCs, you can literally put, I mean, thousands and thousands of such logical functions merely in computer memories. So they are, in terms of speed, size, complexity, and even reliability, they are beating their relay counter. They have already beaten, no question of beating. They have already beaten their relay counterparts hands down. It's a very old technology actually. Nowadays hardly anybody uses it. In fact, all the time, anywhere you go to any factory, you will find tens of PLCs all around. So what is a PLC? What does it do? We have understood that it's a, actually, you know, I looked at the internet and tried to locate some definitions of the PLC, and these are some of the definitions which I found on the internet, but somehow I didn't like them. So somebody says it's a solid state device designed to perform logic functions. Solid state device, the term is actually not very communicative, because it describes everything is a solid state device. Even a small transistor is also a solid state device. So solid state device designed to perform logical functions, what's previously accomplished by electromechanical relays. This is something which mentions the history. Devices used for control, operation, and integration of manufacturing processes. Yes, this is, I like it more, of manufacturing process equipment and machinery, but it does not say what kind of device these are. It is very cryptic on the device side. An assembly of digital logic elements. This word element is very confusing. What is meant by digital logic elements? Designed to make logical decisions. So, you know, designed to make logical decisions and provide outputs. So I thought that I'll find out my own definition. So I'm calling it an industrial computer. It's actually a computer which is used for industrial functions. What kind of functions? Which will accept inputs from digital or analog sensors, which will execute logic for sequence control or analog control. In fact, modern PLCs in many cases also contain capabilities for doing analog controls on the same device. After all, it's a microprocessor, so you can have several. Its speed is very high. It has a lot of memory. So why not also, since you are buying a device, why not put the analog controls also? Otherwise, you will have to buy another device just for analog controls. So while logically they are different, physically speaking, one single PLC box can house even analog controllers. In fact, they do. They could drive actuators or indicators, or they could communicate with other computers. So what are these components? Its components are typical of a computer. So you can have the sort of the backplane, or you can have a power supply, or you can have CPU memory, or you have IO cards. Various kinds of IO cards are used. So you can have digital or analog modules. You can have some special purpose function modules like high speed counters which measure shaft angle encoder which measure rotational speeds, or certain very fast and precise positioning commands can be generation modules, PWM generation modules, etc. So various kinds of cards it uses. So obviously there is wiring, and then you need two other separate devices with PLC mainly for for interacting with it. One of them is a programmer using which you can download the PLC, or you can see how variables are getting changed, and the other is a man-machine interface which can display some of the variables nicely so that people can see how things are being controlled. So actually we will make I have a little change of plan in this thing. Since time is nearly up, so I would skip the programming part in this lesson, and then we'll include it in the next lesson. So I'm going to skip the next few slides and then come directly to the lesson review. Okay. So all these things we'll so we are going to see all these things in the next class, which I thought I will include here, but there's no time. Okay. So yeah. So we have the lesson review. So what have you seen? So in this lecture we have primarily tried to impress upon you the nature of discrete event control problems. Basically two things, that there are some problems where analog controls are not required because they are too simple. If you start a motor for a conveyor, you don't need to control its speed. Just put full voltage, whatever speed it will rotate, let it rotate, conveyor will move. We are not interested in controlling the speed in an analog manner. These are situations where analog logic control is used. There are another kind of situations where you are trying to design the control at a supervisory level. So there is a whole set of sophisticated analog controllers existing, and the moment you give them a command, you know that they will realize them. How they will realize is not your concern, as long as you are designing at the supervisory level. So because you are designing at the supervisory level, your control problem is abstracted out. So in that sense it is discrete event. So we have seen that many such problems arise in the context of industry, and we are going to, in this module we are going to take a look at how we will handle them. So we also introduced the programmable controller. We gave it functional definition, and we saw what it contains. It's basically a microprocessor based device with a lot of interfacing capabilities. And this PLC programming basics we actually did not consider in this lecture, and we'll be considering in the next one. So you could do several things. For example, you could find a typical industrial example. Let's see, for example, you can see things like, I'll give you one example myself and you can think of others. For example, think of how to automate the overhead tank in your house using maybe some level sensors and a motor and a pump such that the water level never goes below a certain level. So, you're never surprised in the kitchen. So, try to model the system, identify its input, outputs and state variables, develop its finite state machine model, and then finally can you draw a, you can't do this now, but you can perhaps figure out that how based on the feedback you are going to apply the different kinds of controls. So, construct an example of your own, that is the assignment, and that is all for today. Thank you very much. From the next class we will start with the programming aspects of PLCs. Thank you. Good afternoon and welcome to lesson number 19, where we shall continue to discuss sequence control. Today we will discuss a scan cycle, that is a scan is a program execution. So, we will discuss how programs are cyclically executed, and we will discuss the nature of its impact on performance, and we will also discuss how to write some simple relay ladder logic programs. So, as usual we view the instructional objectives first. After today's lesson, one should be able to describe a typical program scan cycle, that is describe what takes place, how the program works cyclically, would be able to explain the impact of this kind of execution on the control performance, typically on the fastness of response, that is how fast the programmable logic controller responds to changes in inputs with changes in output. Then we will go on to describe the basic elements of a typical relay ladder logic program. Today we will look at the very simple elements of the program, and in future lectures we shall go on to see more advanced programming elements.